Okay, let's unpack this. We've got a fantastic set of source material here, diving deep into the world of deep learning questions in theory.
Yeah, quite a collection.
Think of this as your personalized shortcut to getting a handle on, well, a whole range of fundamental concepts. Everything from data types, optimization.
All the way to machine learning methods, neural network bits and pieces, and even robotics and computer vision geometry.
Exactly. Our mission in this deep dive is really to pull out the most important nuggets of knowledge from these sources, connect the dots for you.
And hopefully give you that clear structure without, feeling totally overwhelmed by all the information.
That's the plan. We'll cover the basics first: AI, ML, DL, then learning types, algorithms.
Right. We'll touch on some key linear algebra and probability concepts, too, because you kind of need those. Then dissect the building blocks, neurons, cost functions, backprop.
And then get into more advanced topics like transformers, reinforcement learning.
And even look at how these ideas actually get applied in things like robotics and computer vision. It's quite a journey, really, into how these systems tick.
So where do we even start with a field this massive? The sources seem to suggest beginning with the big picture.
Absolutely. Makes sense. So at the highest level, you've got artificial intelligence, AI. That's the broad goal, right?
Yeah.
Creating systems that can do tasks needing human intelligence.
Kind of mimicking human behavior.
That's the grand ambition. Yeah.
And nested inside AI, machine learning.
Exactly. ML is a subset. It uses statistical methods, basically lets systems learn from data without you having to program every single rule explicitly.
So instead of writing rules, you just give it data and an algorithm.
That figures out the patterns itself. Gets better with experience.
And then right at the core, the thing enabling a lot of the really powerful systems today is deep learning.
Right. DL. It's a subset of ML again. What makes it deep is these multi-layer neural networks. Lots of hidden layers.
Which used to be computationally impossible to train.
Pretty much, yeah. But breakthroughs
Yeah.
made it feasible. Think of those concentric circles you sometimes see. AI is the biggest circle, ML is inside that, and DL is that dense core.
That visual definitely helps. Okay, within AI, the sources mention different categories.
They do. You've got artificial narrow intelligence, or ANI, sometimes called weak AI, designed for just one specific task.
Like AlphaGo playing Go or facial recognition.
Spot on. Then there's the theoretical goal of strong AI. That's systems with human-like general reasoning, across different tasks. Doesn't really exist yet.
And the final one, ASI.
Artificial superintelligence, hypothetical stuff. Systems smarter than humans. Definitely doesn't exist now.
Got it. Okay, let's zoom back into machine learning specifically. Some foundational terms we should probably cover. An algorithm. That's like the recipe.
Yeah, the recipe. The set of rules or statistical techniques used to learn from the data.
And applying that algorithm to data during training,
Yeah,
that gives you the model.
right. The model is the result, the learned function or representation that the algorithm spits out.
Okay. And in your data, variables have different roles.
You've got the predictor variable or feature. That's the input data you use to make a prediction.
It's like square footage of a house.
Exactly. And then the response variable or target variable. That's the output you're trying to predict.
The house price.
Right. Simple distinction, but super important.
Okay, now let's talk about how these models actually learn. The sources categorize machine learning into a few main types.
Yeah. The most common one is probably supervised learning. The key thing here is you train it with labeled data, annotated data.
Meaning you give it the inputs and the correct outputs.
Exactly. Input-output pairs. The model learns the mapping between them.
So the house price example again, I give it square footage, number of bedrooms, and the correct sale price for lots of houses.
Precisely. And that specific example is regression within supervised learning. The output is a continuous number, like a price or temperature.
And the other main type is supervised problem.
Classification, where the output is a category, like spam or not spam for email.
Or cat or dog for an image.
You got it.
And supervised learning. That's the one where you can often use A/B tests to check how well it's doing in the real world.
Yeah, exactly. Especially when you deploy them. Good way to test.
Okay, but what if you don't have those labels? What if the data is just raw?
Ah, right. That's unsupervised learning. You give the model unlabeled data, and its job is to find hidden patterns or structure within it, all by itself.
Like grouping similar customers together. Or spotting weird transactions.
Yes, exactly. Clustering is a big one, grouping similar data points, like customer segmentation or finding potential fraud, because it clusters differently from normal transactions. And association rule mining is another, finding things that often occur together.
Yeah.
People who bought X also bought Y, that kind of thing.
Right, market basket analysis. And the third main type?
Reinforcement learning, RL. This is different again. Here, an agent learns by interacting with an environment.
Trial and error.
Pretty much. It takes an action, gets a reward or maybe a penalty based on the outcome, and learns over time to choose actions that maximize its total reward.
Like training a robot to walk or a game AI.
Perfect examples. That table comparing regression, classification, and clustering is pretty handy, actually.
Yeah, the one showing supervised versus unsupervised, continuous versus categorical, and the main goal. Forecasting, categorizing, clustering.
It boils down the core differences nicely. Okay, shall we unpack some specific methods now? Maybe start with supervised learning ones.
Sounds good. We mentioned linear regression. Simple, predictable.
It is, yeah. Foundation stuff. Predicts a continuous dependent variable, y, based on independent variables, x, by fitting a straight line, basically. The formula is simple. Y, BO plus B1x plus E. Good for prediction and just understanding linear relationships.
Okay, then there's logistic regression. Sounds similar, but you said it's for classification. How does it work for categories?
Right, so the key difference is the sigmoid function. Instead of predicting the value directly, logistic regression models the probability that the output belongs to a certain class, let's say class 1.
Yeah.
It uses that S-shaped sigmoid curve, which takes any real number and squishes it into a value between 0 and 1. Perfect for probability.
Ah, so the output is a probability.
Exactly. And that S-shape is important too, because small changes in the input lead to small changes in the output probability, which helps with learning.
So you get a probability and then maybe set a threshold like 0.5 to decide yes or no.
That's the usual way, yep. And if you have more than 2 classes, you can use methods like one versus all or multinomial logistic regression.
The sources mentioned the logit function too.
Ah, yeah, the logit. It's just the inverse of the sigmoid. It maps probabilities, which are between 0 and 1, back to the full range of real numbers. It's kind of the mathematical trick that lets us connect linear models to these probabilities. LNP, 1P.
Clever. Twisting a linear idea for categories. Okay, what about decision trees? They seem intuitive.
Very interpretable, yeah. You start at the root node, ask a question about a feature.
Like, is feature X greater than 5?
Right. And based on the yes-no answer, you follow a branch down to the next node, ask another question, and keep going until you hit a leaf node.
And the leaf node gives the prediction.
Exactly, the classification or the regression value. The sources mention the ID3 algorithm, which is one way to choose the best question to ask at each split point. It tries to maximize information gain.
Information gain, like reducing uncertainty.
Basically, yeah. How much does knowing the answer to this question reduce the uncertainty about the final outcome? It uses entropy to measure that.
And you said they can do regression too.
They can. Instead of maximizing information gain, you'd minimize something like variance or standard deviation within the branches for continuous outputs.
But the big problem with single trees is overfitting.
Yeah, that's the classic issue. A single decision tree can get really complex, basically memorizing the training data, noise, and all. So it does great on the data it saw, but poorly on new, unseen data.
Which brings us neatly to random forests. I'm guessing the forest involves multiple trees.
Spot on. Random forests combat that overfitting by building many decision trees, not just one. An ensemble.
How does having many trees help?
Well, each tree is trained on a slightly different random subset of the training data. This uses a technique called bagging, or bootstrap aggregating.
Bootstrapping. That's sampling with replacement.
Yes. So each tree sees a slightly different version of the data. Often there's randomness in choosing which features to consider at each split, too. Because the trees are built on different data, and with some randomness, they tend to make different kinds of errors.
Ah, so they don't all overfit in the same way.
Exactly. And when you combine their predictions, maybe averaging for regression or taking a majority vote for classification, the errors tend to cancel out, and you get a much more robust model that generalizes better. Strength in numbers.
Like getting a second, third, and fourth opinion instead of just trusting one expert who might have biases.
Great analogy. Okay, next up, naive Bayes. Probability involved here, right?
Yeah.
Naive. Yep, it's based on Bayes' theorem, which is fundamental for updating probabilities with new evidence. The naive part is its big assumption. It assumes all the predictor variables are independent of each other, given the class.
Independent, like the presence of one word in an email has no bearing on the presence of another word if we know it's spam.
That's the assumption, yeah.
Yeah.
Which in reality is almost never true, right?
Yeah.
Words are definitely dependent.
Yeah.
But the model often works surprisingly well, despite this simplification.
Why use it then if the assumption is flawed?
It's very computationally efficient, fast to train, and works well, especially with high-dimensional data like text. The sources call it a parametric model because it makes this strong assumption about the data structure, independence, and estimates a fixed number of parameters based on that.
Okay, last supervised method for now. K, nearest neighbor. KNN.
Right, KNN. This one's different again. It's non-parametric. It doesn't learn a fixed set of parameters or assume a specific shape for the decision boundary.
How does it work then?
When you get a new data point you want to classify, KNN looks at the K training data points that are closest to it in the feature space its nearest neighbors.
Based on distance, like Euclidean distance.
Usually, yeah. Then it just assigns the new point the class that's most common among those K neighbors.
Yeah.
Simple majority vote.
So, it doesn't really train by building a model beforehand. It just stores all the data.
Exactly. That's why it's often called a lazy model. All the work happens at prediction time, when it has to calculate distances to find the neighbors for every new point.
Which could be slow if you have tons of training data.
Can be, yeah. And another thing, it's sensitive to the scale of your features. If one feature has a much larger range than others, it can dominate the distance calculation. So scaling your data is usually important for KNN.
Good point. And you contrasted this with k-means earlier.
Yeah, gotta be careful with the names. KNN is supervised. For classification or regression, it's lazy, non-parametric, and scale-sensitive. K-means is unsupervised. For clustering, it's eager because it computes centroids during training, also non-parametric, but maybe less sensitive to scale in the same way, though scaling can still help.
Okay, let's shift gears to k-means then. Unsupervised clustering.
Right, so K-means tries to partition your unlabeled data into a specific number, K, of distinct groups or clusters. The main goal is to minimize the within-cluster sum of squares, or WCSS.
WCSS, what does minimizing that actually mean?
It means you want the data points within each cluster to be as close as possible to the center of that cluster, the centroid. You're trying to make the clusters tight and compact.
Makes sense, but how do you know what K should be? How many clusters to aim for?
Ah, good question. The elbow method is a common heuristic. You run K-means for several different values of K, say, K1, K2, K3, and so on. For each K, you calculate the WCSS, or sometimes called sum of squared errors, SSE.
And then you plot it.
Yep. Plot WCSS against K. As you increase K, the WCSS will naturally go down more clusters, means points are closer to some centroid. But usually, the drop slows down significantly at some point. That point on the graph where the rate of decrease sharply bends looks like an elbow is often considered a decent choice for K.
Because adding more clusters after the elbow gives less bang for your buck, so to speak.
Exactly. Diminishing returns.
The color compression example in the sources was pretty cool, using k-means to reduce millions of image colors down to just 16 representative ones.
Yeah, it's a great visual. Shows how k-means can find that underlying structure and simplify the data, the 16 average colors, while keeping the image looking pretty similar. Okay, should we move on to optimization concepts? These are super important for actually training models, especially the deep ones.
Right. First order versus second order optimization. What's the deal there?
So first order optimization methods think gradient descent, and its variations, they only use the gradient, the slope, the direction of steepest descent. Second order optimization, on the other hand, uses the Hessian matrix. That's the matrix of second partial derivatives. It tells you about the curvature of the loss function at a point.
Like whether it's curving up like a bowl or down like a hill or something else.
Exactly. The eigenvalues of the Hessian tell you that. If all eigenvalues are positive at a point where the gradient is 0, you're at a local minimum. All negative, a local maximum.
And if it's a mix?
A mix of positive and negative eigenvalues. That's a saddle point.
Saddle point? It sounds problematic for optimization. Like you're flat in some directions, but curved up or down in others.
Precisely. The gradient is 0, so first-order methods might stop. But it's not a true minimum or maximum. Second-order methods can see the mixed curvature.
So if second-order methods give you more info about curvature, why aren't they the standard for deep learning? Seems like they'd be better.
You'd think so, right. Yeah. But there are major practical problems. First, computing and storing the Hessian matrix is incredibly expensive. For a model with millions or billions of parameters, the Hessian is huge. Think n squared parameters, where n is the number of model weights. Just infeasible.
Ah, the computational cost.
Big time. Also, they can be more sensitive to noisy gradients, which you often get with large data sets. And in the very non-convex landscapes of deep learning, they can sometimes get stuck in local optima or those saddle points more easily than first-order methods with momentum. Plus, they often have more hyperparameters to tune.
So first-order methods like SGD and Atom are the workhorses because they're just more practical at scale.
Pretty much, yeah. They strike a better balance between progress and computational feasibility for these massive models.
Okay, let's get into the core building blocks of deep learning, starting with the neurons. Perceptrons versus sigmoid neurons.
Right. A basic perceptron is like a simple threshold unit. Takes inputs, weights them, sums them up. If the sum beats a threshold, output is 1, otherwise 0. Binary output.
Like an on-off switch.
Kind of, yeah. They can function like simple logic gates, NAND gates, for example.
But that 0 or 1 output, it's discrete, hard to learn with gradients.
Exactly. That's the key limitation. A small change in a weight might not change the output at all, or it might flip it suddenly from 0 to 1. There's no smooth gradient signal telling you how to adjust the weight.
And that's where sigmoid neurons come in.
Right. Instead of a hard threshold, a sigmoid neuron passes that weighted sum through the sigmoid function. We saw that S-curve before. It outputs a continuous value between 0 and 1.
And that continuous output is the crucial part for learning.
Absolutely. Because the output changes smoothly with changes in weights and biases, you can calculate a meaningful gradient. Small weight adjustments lead to small output changes, allowing gradient descent to work its magic and nudge the weights in the right direction to reduce error. Multilayer perceptrons, despite the name, typically use neurons like sigmoid or other smooth activations precisely for this reason.
Makes total sense. Smoothness enables learning. Okay, so we need to measure that error cost functions.
Yep, cost functions, or loss functions, quantify how wrong the model's predictions are compared to the actual target values. For gradient-based learning to start easily, you want a cost function that's smooth, like mean squared error, MSE, the quadratic cost.
Why is smoothness important here, too?
Well, its derivative needs to be well behaved. With MSE, the derivative is proportional to the error, which is nice and smooth. Something like mean absolute error, MAE, while maybe less sensitive to outliers, has a derivative that isn't smooth at 0, which can sometimes cause issues for gradient methods initially. MSE penalizes big errors more heavily because of the squaring.
But you hinted earlier that other cost functions are actually better for classification tasks, especially with sigmoid outputs.
Definitely. MSE has this issue called learning slowdown when used with sigmoid neurons in classification. Imagine the neuron is very confidently wrong. Its output is close to 0 when it should be 1, or vice versa. In those regions where the sigmoid output is near 0 or 1, the sigmoid curve is very flat. Its derivative is tiny. Since the gradient of the MSE cost involves the derivative of the activation function, the cost gradient also becomes tiny.
So even if the error is huge, the update signal to the weights is minuscule. Learning just crawls.
Exactly. It's incredibly frustrating. That's where cross-entropy cost function comes in. Or log likelihood, often paired with softmax.
How do they fix the slowdown?
Their gradients are structured differently. When you combine cross-entropy loss with a sigmoid or softmax output layer, the derivative of the activation function effectively cancels out in the gradient calculation for the weights leading into that layer. The resulting gradient ends up being directly proportional to the output error itself.
Ah, so if the error is big, the gradient is big and learning is fast. If the error is small, the gradient is small.
Precisely. It avoids that saturation problem and makes learning much more effective, especially in the later stages of training. Cross-entropy essentially measures the difference between the predicted probability distribution and the true one-hot distribution.
And softmax for the final layer, when to use that instead of multiple sigmoids.
Softmax is generally preferred when you have a multi-class classification problem, where the classes are mutually exclusive and input belongs to exactly one class, PNG digit recognition 09. Softmax takes the outputs for all classes and turns them into a probability distribution that sums to 1.
So it gives you the model's confidence across all options relative to each other.
Right. Whereas multiple independent sigmoids would give you a probability for each class independently, and they wouldn't necessarily sum to 1. Could be useful if an input can belong to multiple classes simultaneously, multi-label classification. The table in the sources gives good recommendations. Regression usually uses a linear output and MSE loss, binary classification, sigmoid and binary cross-entropy, multi-class, single label, softmax and cross-entropy log likelihood, multi-label, sigmoid and binary cross-entropy again.
That table's super helpful. Okay, we have a cost function. Now, how do we actually minimize it using those nice gradients? Gradient descent.
Right, gradient descent is the workhorse optimization algorithm. Think of the cost function as a hilly landscape, and you want to find the bottom of the valley. Gradient descent tells you which direction is downhill, the negative gradient, and takes a step in that direction.
And you keep taking steps until you reach the bottom, hopefully.
That's the idea. But how you calculate that gradient and take the step leads to different flavors.
Like batch, stochastic, and mini batch.
Exactly. Batch gradient descent calculates the gradient based on the entire training data set before taking a single update step. It gives you the true gradient direction for the whole data set, so it's stable, but incredibly slow. For large data sets, you have to process everything for one tiny step.
Impractical for big data.
Totally. Then there's stochastic gradient descent, SGD, at the other extreme. It calculates the gradient and updates the weights using just one randomly chosen data point at a time.
Much faster updates.
Way faster.
Yeah.
But the path it takes towards the minimum is very noisy, kind of zigzagging all over the place, because each update is based on just one example.
Does that noise ever help?
It can, actually. That randomness can help it jump out of shallow local minima that batch GD might get stuck in. Also good if your data is changing over time. Online learning.
And the middle ground.
Mini-batch gradient descent. This is the standard for deep learning. You use a small batch of data points, maybe 32, 64, 128, something like that, to calculate the gradient and update.
So faster than batch, but smoother than pure SGD.
Precisely. It balances the speed of SGD with the stability of batch GD. You get a reasonably good estimate of the overall gradient from the mini-batch, allowing for more stable convergence than SGD, but you're still making frequent updates, so it's much faster than batch GD. Plus, it leverages hardware optimizations for matrix operations well.
Makes sense. A good compromise. Okay, so gradient descent tells us which way to step. But how do we efficiently calculate those gradients for all the weights and biases in a potentially very deep network? That's backpropagation, right?
Exactly. Backpropagation is the algorithm that does this efficiently. It's basically a clever way to apply the chain rule from calculus to compute the gradient of the cost function with respect to every single parameter in the network.
Working backwards from the output.
Yep. It calculates the error at the output layer, then propagates this error signal backward through the network, layer by layer. At each layer, it figures out how much the weights and biases in that layer contributed to the error, allowing gradient descent to know how to adjust them.
So it's not the learning algorithm itself, but the engine for calculating the gradients that gradient descent needs.
Perfect way to put it. The sources mention a couple of assumptions about the cost function needed for backprop to work cleanly.
Oh, yeah.
First, the total cost should be calculable as an average of the costs for each individual training example. Second, the cost for one example should be expressible as a function of the network's final output activations for that example. These just make the math work out nicely for the backward pass.
And the sources mention some fundamental equations, BP1 to BP4.
Yeah, they lay out the core math. BP1 relates the error in a layer to the error in the next layer. BP2 gives the gradient with respect to the bias. BP3 gives the gradient with respect to the weight. And BP4 is interesting. It shows how the gradient for a weight depends on the activation of the neuron feeding into that weight. It implies that neurons with low activation learn slowly, connecting back to that saturation issue with sigmoids.
Right, all ties together. Okay, so we have the mechanism, but training deep networks is still hard. What are some key ways to improve neural network learning?
The sources list several crucial techniques. We've already touched on using better cost functions, like cross-entropy. Then there's regularization methods to fight overfitting. Better initialization of weights is critical, and of course, good hyperparameter tuning.
Let's talk about regularization. Overfitting is when the model learns the training data too well, including noise, right? How does penalizing weights help?
Exactly. Regularization adds a penalty term to the cost function based on the size of the weights. The idea is to discourage the model from relying too heavily on any single feature or learning overly complex functions that just fit the noise.
So L2 regularization, that's weight decay.
Yep, L2, also called ridge regression in linear models, or weight decay. It adds a penalty proportional to the sum of the squares of all the weights. This encourages the network to use smaller weights overall. Smaller weights generally lead to simpler, smoother functions that are less likely to overfit the training data's quirks.
And L1 regularization, lasso.
L1 adds a penalty proportional to the sum of the absolute values of the weights. The interesting effect of L1 is that it encourages sparsity. It tends to drive many of the weights to become exactly zero.
So it effectively performs feature selection, forcing the model to ignore some inputs.
Precisely. If a feature isn't very useful, L1 is more likely than L2 to just zero out its corresponding weight. L2 tends to make all weights small, but keeps most of them non-zero.
So L1 for sparsity and feature selection, L2 for generally smaller weights and maybe smoother models.
That's a good summary. L2's derivative is also smoother than L1's, which isn't smooth at zero, which can sometimes be beneficial for optimization.
And how does this connect to the bias-variance trade-off?
Regularization is primarily a tool to reduce variance. High variance means the model is overly sensitive to the specific training data. It changes a lot if you train it on a slightly different data set that's overfitting. By constraining the weights, regularization makes the model less sensitive, reducing variance and improving generalization to unseen data.
But there's a trade-off.
Right. Usually, this reduction in variance comes at the cost of a small increase in bias. Bias is how much the model's average prediction differs from the true value. A slightly simpler model might not fit the training data quite as perfectly, higher bias, but its better generalization, lower variance, makes it perform better overall on new data.
Okay, moving on. Weight initialization. Why is just starting the weights off randomly not always good enough?
It's incredibly important how you start. If you initialize weights too large, the signals passing through the network can blow up, leading to exploding gradients and unstable training. If you initialize them too small, the signals can shrink rapidly as they pass through layers, leading to vanishing gradients where learning just stops.
So you need that Goldilocks zone.
Exactly. Good initialization strategies aim to set the initial weights such that the variance of the activations and gradients remains roughly constant as signals propagate forward and backward through the network layers. The simple Gaussian initialization, mean 0 SED dev 1 n, where 9 is the number of inputs to the neuron, is a basic attempt.
But there are more sophisticated methods like Xavier-Glorot and He.
Yes, Xavier-Glorot initialization is designed to work well with activation functions like sigmoid and tan. He initialization is specifically designed for ReLU and its variants, accounting for the fact that ReLU kills half the signal, the negative part.
And others mentioned?
Orthogonal initialization can be useful, especially in recurrent networks or RL. Using pre-trained weights from a model trained on a large data set, like ImageNet, is standard practice for transfer learning, gives you a huge head start. Uniform initialization is another option. And layer normalization, while technically applied during training, helps stabilize activations layer by layer, especially in deep networks like transformers. The tables provide a good guide for which strategy might fit which architecture or activation.
We keep mentioning activation functions. We saw sigmoid. The sources had that nice table with plots of others like ReLU.
Right. Identity just outputs the input, linear. Tan H, like sigmoid, but output range is Meganit 1-to-1. ReLU, rectified linear unit, became super popular outputs, the input at positive, 0 otherwise. Very simple, computationally cheap, and helps alleviate the vanishing gradient problem for positive inputs compared to sigmoid time.
And variants like pre-ReLU, ELU.
The pre-ReLU, parametric ReLU, learns the slope for negative inputs instead of it being 0. ELU, exponential linear unit, becomes negative for negative inputs, but the saturates smoothly, which can sometimes help. Soft Plus is a smooth approximation of ReLU. Choosing the right activation is often empirical, but ReLU and its variants are very common defaults now.
Got it. The sources also had some practical formulas for calculating things like the output size of a convolution layer.
Yeah, useful for designing networks. The output size depends on the input size, W, the filter size, F, the padding P added around the border, and the stride, S, the filter moves by. The formula is usually something like WF plus 2PS plus 1.
And calculating the number of parameters.
Also important for understanding model complexity and computational cost. For a convolutional layer, it depends on the filter size, the number of input channels, and the number of output channels, filters. For a fully connected layer, it's basically the number of input neurons times the number of output neurons, plus the biases for the output neurons. The examples show how quickly parameters can add up.
Okay, that covers the deep learning building blocks pretty well. Let's pivot to some of the essential math that underpins a lot of this, linear algebra and probability.
Can't escape the math. A key concept from linear algebra is eigenvalues and eigenvectors. Remember those?
Vaguely. An eigenvector is a vector that a matrix transformation doesn't change the direction of, only scales it.
That's the essence, yeah. The matrix transformation just stretches or shrinks the eigenvector by a factor, and that factor is the eigenvalue.
We saw they're used with the Hessian in optimization. Where else are they critical?
They're fundamental to understanding the principal axes of linear transformations in data. They are the core component of principal component analysis, PCA.
Okay. And thinking about relationships between variables, covariance and correlation.
Right. Covariance measures how two variables change together. Positive covariance. They tend to go up or down together. Negative. One goes up as the other goes down.
But the value itself is hard to interpret. Like, is a covariance of 50 big or small?
Exactly. It depends on the units and scales of the variables themselves. That's why correlation is often more useful.
Because it's normalized.
Yep. Correlation takes covariance and normalizes it, usually by standard deviations of the variables. This gives you a value strictly between -1 and +1. It measures the strength and direction of the linear relationship, and it's unitless, unaffected by changes in scale. +1 is perfect positive linear, perfect negative linear, 0 is no linear relationship.
Important note, linear relationship. They could have a nonlinear relationship and still have zero correlation.
Absolutely critical point. Both covariance and correlation only capture linear association, and they're both unaffected if you just shift the data at a constant to all values.
And the covariance matrix just bundles this up for multiple variables.
Yeah, it's a square matrix where the diagonal elements are the variances of each individual variable, and the off-diagonal elements, cov-aj, are the covariances between pairs of variables. Super useful in multivariate statistics.
Which brings us back to PCA, principal component analysis, dimensionality reduction.
Right. PCA aims to find a lower dimensional representation of your high-dimensional data while preserving as much of the original variance information as possible. It does this by finding the directions of maximum variance in the data. These directions are the principal components, and they turn out to be the eigenvectors of the covariance matrix of the data.
So you calculate the covariance matrix, find its eigenvectors, and the ones corresponding to the largest eigenvalues capture the most variance.
That's one way, yeah. PCA via eigendecomposition of the covariance matrix. The forces also mentioned you can achieve the same result using singular value decomposition, SVD, on the center data matrix. The right singular vectors, v from m equal u sigma vt, give you the principal directions.
SVD sounds like another powerful matrix tool.
It is. Singular value decomposition factorizes any matrix M into U sigma, Vt. U and V are orthogonal matrices, and sigma is a diagonal matrix of singular values. It's incredibly versatile, used all over science and engineering.
Okay, shifting to probability. Bayes' theorem. Can't avoid that one.
Fundamental. It tells you how to update your belief, probability, about a hypothesis A, given some new evidence B. The formula, PAB equals PVA times PA divided by PB. The probability of A given B depends on the probability of B given A, the prior probability of A, and the overall probability of B.
And it's the engine behind the naive Bayes classifier we discussed.
Exactly.
The sources also briefly mentioned Dirichlet distribution and KL divergence.
Yeah, Dirichlet is a distribution over probability distributions, basically. Useful for modeling things like the proportions of topics in a document. Kullback-Leibler, KL divergence, is a way to measure how different one probability distribution is from another. It's not strictly a distance metric, it's not symmetric, but it quantifies the information lost when approximating one distribution with another. Yeah. Used a lot in variational autoencoders, for example.
Got it. Finally, a really practical data prep step, standardization versus normalization. What's the difference again?
Often confused. Normalization typically means rescaling your data features to a fixed range, most commonly 0, 1. You do this usually by subtracting the minimum value and dividing by the range, maxband.
Okay, simple enough. Downsides.
It's quite sensitive to outliers. A single very large or very small value can drastically squash all the other data points into a tiny part of the 0, 1 range. It's often used when you know your data has specific bounds, or maybe for algorithms that expect inputs in that range.
And standardization?
Standardization rescales data so that it has a mean of 0 and a standard deviation of 1. You do this by subtracting the mean and dividing by the standard deviation for each feature.
So it centers the data at 0.
Right. It doesn't constrain the data to a specific range like 0, 1, but it gives it standard properties. 0 mean unit variance. It's generally less sensitive to outliers affecting the range, although outliers will still affect the calculated mean and standard deviation.
When would you prefer standardization?
It's often preferred for algorithms that assume data is centered around 0, or algorithms that rely on distance calculations, like KNN, SVM, PCA, as it prevents features with larger variances from dominating. Also common when using pre-trained models, which often expect standardized inputs. The comparison table is a good reference.
Okay, that's a solid foundation. Ready to dive into reinforcement learning, RL, in more detail.
Let's do it. So remember the core loop. You have an agent, the learner or decision maker.
Like the robot or the game player?
Right. It exists in an environment. It observes the current state of the environment. Based on that state, it chooses an action, according to its policy.
The policy is its strategy.
Yeah, its strategy or brain. The action affects the environment, which then gives the agent a reward, could be positive or negative, and transitions to a new state, and the loop continues.
And the goal is to maximize rewards over time.
Maximize the cumulative reward in the long run, yeah. Not just the immediate reward.
Key terms here. We have agent, environment, state, action, reward, policy. What about value?
Value, often denoted Vs, represents the expected total future reward, starting from a particular state and following a certain policy. It's a measure of how good a state is. Action value Q is similar, but it's the expected total future reward starting from state S, taking action A, and then following the policy. It tells you how good a specific action is in a specific state.
Q values. That would sound important.
Very. Especially for value-based RL algorithms, which try to learn the optimal action value function, Q, and then derive the policy from that, i.e. always choose the action with the highest Q value.
What are other types of RL algorithms?
You also have policy-based methods that learn the policy directly without necessarily learning a value function first. Model-based methods try to learn a model of how the environment works, state transitions, rewards, and use that model for planning. Model-free methods, like Q-learning, learn directly from trial and error experience without building an explicit model of the environment.
Okay. And temporal difference, TD learning versus Monte Carlo.
These are ways to estimate values from experience in model-free settings. Monte Carlo methods run through a whole episode, like one full game, collect all the rewards, and then update the value estimates for the states visited based on the total observed return.
So they wait until the end.
Right. TD learning, on the other hand, updates value estimates after each step or action. It uses the currently learned estimate of the next state's value to update the current state's value. It learns from the difference between temporally successive predictions. Q-learning is a TD method.
So Q-learning itself, you said it's model-free, off-policy, TD.
Correct. Model-free learns from experience. TD updates step by step. Off-policy is interesting. It means the policy Q-learning learns about the optimal greedy policy Q can be different from the policy it actually uses to gather experience, the behavior policy, which might be more exploratory, like epsilon greedy.
So it can explore around, but still learn the best possible path.
That's the idea. It learns the Q values for the optimal actions, even if it doesn't always take them during training. Usually for simple problems, these Q values are stored in a big table, a Q table, mapping state action pairs to values.
But the cart pole example, that has continuous states like position, velocity, can't really have a table for infinite states.
Exactly. For traditional Q-learning with a table, you'd have to discretize or bucketize the continuous state space, turn the continuous ranges into a finite number of bins. But this quickly becomes impractical as the number of dimensions grows the cursive dimensionality.
And this is where deep learning comes in again. Deep Q learning, DQN.
Precisely. DQN replaces that Q table with a deep neural network. The network takes the state as input and outputs the estimated Q values for all possible actions in that state.
So it can handle continuous states naturally, just like other neural networks?
Yes, a huge advantage. But using a powerful function approximator like a neural network with RL introduces its own stability challenges.
Right. The sources highlighted two main problems and their fixes in DQN. First, correlated sequential observations.
Yeah. RL data comes in sequences, S1, A1, R1, S2, A2, R2. Training a neural network directly on these highly correlated transitions makes it unstable, like showing a kid only pictures of red cars and expecting them to learn about all cars.
So the fix is experience replay.
Yep. You store these transitions, state, action, reward, next state, in a large memory buffer. Then, for training, you sample random mini-batches of experiences from this buffer. This breaks the temporal correlations and makes the training data look more like the IID, independent and identically distributed data that supervised learning thrives on.
Makes sense. Shuffling the memories. Second problem. Instability from the target value changing constantly.
Right. In the Q-learning update, the target value often depends on the maximum Q value predicted for the next state. If you use the same network you're currently training to predict this target value, the target keeps changing with every update step. It's like chasing a moving target, leading to oscillations and divergence.
How does DQN fix that?
With a separate target network. You maintain a second neural network, the target network, which is a clone of the main Q network.
Yeah.
But its weights are updated only periodically, say, copied from the main network every few thousand steps and kept frozen in between. You use this frozen target network to calculate the target Q values for the updates. This provides a stable target for the main network to learn towards.
Clever tricks to stabilize things. The sources also had some really practical advice on actually selling an RL project to a client.
Yeah, it goes beyond just the cool algorithm. You need to show you've thought about deployment. Things like ensuring node stability, can you reliably collect the data you need from their systems? Having a hardened prototype code that's robust, not just research code. Showing previous incubations or references helps build trust.
And starting small.
Definitely.
Yeah.
Suggest starting with only a small portion of traffic to de-risk the deployment, gather data, and show some initial ROI. And critically, ensure there's actually adequate traffic flow or interaction volume for the RL agent to learn effectively in the real environment. Not enough diverse data, no learning.
Good practical points.
Huh?
Now, a simpler RL setup mentioned was the K-armed bandit or multi-armed bandit problem.
Right, this is like a simplified RL problem where the state never changes. You just have a fixed set of K actions available, like K slot machine levers, the arms. Each action gives rewards drawn from some unknown probability distribution.
And the goal is to figure out which arm pays out the best, on average, over time.
Exactly. The core challenge is the explore-exploit dilemma. Should you pull the arm you currently think is best, exploit here, to maximize immediate reward? Or should you try other arms you're less sure about, explore, in case they might actually be better in the long run?
Balancing learning with earning.
Precisely. The sources mention stationary bandits, where reward distributions don't change, versus non-stationary ones, where they can change over time.
And the real-world examples were strong. Azure Cognitive Services Personalizer and contextual bandits giving big lifts on MSN News and Surface.com personalization.
Yeah, they show that even this simpler bandit framework is really useful for things like optimizing ad choices, news recommendations, UI variations, situations where you have choices, get feedback, and the underlying state is maybe just the user context, which doesn't change based on your action in the same way a full RL environment does.
Okay. Finally, for RL algorithms, PPO, Proximal Policy Optimization, got a special mention.
PPO is a very popular and effective algorithm, known for its stability and good performance, especially in continuous control tasks like robotic simulation. It's an on-policy actor-critic method.
Let's break that down. On policy.
Means it learns from data generated by the current version of its policy. This contrasts with off-policy methods like Q-learning that can learn from data generated by older or different policies, for example, from experience replay. On-policy methods typically need to collect fresh data frequently as the policy updates.
And actor-critic.
Means it has two main components, or networks. The actor learns the policy, it decides which action to take in a given state. The critic learns a value function, it estimates how good a state or state-action pair is. The critic's job is to help the actor learn better, often by providing an estimate of the advantage function, how much better an action is compared to the average action in that state, which reduces the variance of the policy gradient updates.
Okay. And the key innovation in PPO is the clipped surrogate objective.
That's the heart of it, yeah. It modifies the objective function used to update the policy. It calculates the ratio of the probability of an action under the new policy versus the old policy. Then it clips this ratio to prevent it from getting too far from 1, either too large or too small. This clipping ensures that the policy updates don't change the policy too drastically in a single step, which is a common cause of instability in other policy gradient methods. It keeps the updates proximal.
So stability is the main benefit.
Stability on relative simplicity, yes. It also tends to be quite sample efficient compared to simpler policy gradient methods, partly because it can perform multiple optimization steps on the same batch of data, multi-epoch updates. It uses first-order optimization, making it easier to scale. Sometimes includes an entropy bonus to encourage exploration.
Got it. Okay, switching domains now to computer vision, CV, starting with the fundamentals, the pinhole camera model.
The simplest abstraction of how a camera forms an image. It's based on perspective projection light rays from a 3D point travel in straight lines through a single point, the pinhole or camera's optical center, and land on the 2D image plane behind it.
And there's a mathematical pipeline for this projection, from world to image.
Yep. You start with a point in 3D world coordinates. First step is to transform it into the camera's coordinate system. This involves rotation and translation to align with the camera's viewpoint. This transformation is captured by the extrinsic matrix, often written as R key, combining a 3x3 rotation matrix R and a 3x1 translation vector T.
Okay, so now the point is relative to the camera.
Right. The next step is to project this 3D point in camera coordinates onto the 2D image plane. This projection depends on the camera's internal characteristics, its focal lengths, fx, s per phi, and the location of the principal point, cx, si, where the optical axis hits the image plane. These are combined into the intrinsic matrix, K.
And applying k gives you the final 2D image point coordinates.
Exactly, usually in pixel coordinates. The overall equation ties it all together. XX, k car t, at, agw, where xw is the 3D world point in homogeneous coordinates, x is the 2D image point, homogeneous, k is intrinsics, rt is extrinsics, and s is a scaling factor related to depth. That's the core projection math.
Okay. Building on that, stereogeometry, using two cameras to get depth.
Right. If you have two cameras viewing the same scene from slightly different positions, a stereo pair, you can figure out the 3D structure, including depth, by triangulating corresponding points seen in both images.
Key geometry concepts here, epipolar lines.
Yeah. Imagine the 3D point P and the two camera centers C1 and C2. These 3 points define a plane called the epipolar plane. The intersection of this plane with the two image planes defines the epipolar lines. If you see point P projected at P1 in image 1, its corresponding point P2 in image 2 must lie somewhere along the epipolar line associated with P1. This constraint drastically simplifies the search for matching points.
And the epipolar point.
Those are just the projection of one camera center onto the other camera's image plane. All epipolar lines in an image pass through the epipolar point in that image.
Now, the fundamental matrix F and essential matrix E capture this relationship mathematically.
They do. They relate the coordinates of corresponding points, P1 and P2, in the two images without needing the 3D point P. The fundamental matrix F is a 3x3 matrix such that for any pair of corresponding points x and x, the equation xtfx equals 0 holds. You can estimate F directly from pixel correspondences. You need at least 7 or 8 points, even if you don't know the camera intrinsics.
And the essential matrix E.
The essential matrix E is related to F but works with normalized image coordinates, points as if taken by a camera with K identity matrix. It specifically encodes the relative rotation R and the direction of the translation T between the two cameras. E is related to F by the intrinsic matrices, E equal KT FDT. So if you know K and K, you can get E from FE, has special mathematical properties related to R and T.
So how does this geometry lead to calculating depth?
The key is disparity. For a given 3D point, disparity D is the difference in its horizontal position, usually, between the left and right images. There's a fundamental relationship. Depth, Z, is approximately proportional to the camera's focal length, F times the baseline, B, the distance between the two camera centers, divided by the disparity D. So ZFBD.
And the crucial takeaway.
Depth is inversely proportional to disparity. Closer objects have larger disparity, farther objects have smaller disparity. Also, a wider baseline B leads to larger disparities for the same depth, which generally makes depth estimation more accurate, especially for distant objects.
But finding those corresponding points accurately, that's the hard part. Stereo matching.
That's the core challenge, yeah. Problems include regions with no texture, hard to match, repetitive textures, ambiguous matches, occlusions, points visible in one eye but not the other, and radiometric differences, lighting, exposure changes between views.
The foreshortening effect was also mentioned?
Right. A patch of surface viewed from two different angles might appear distorted or scaled differently in the two images. This can make simple patch comparison difficult, sometimes requiring geometric warping before comparison.
And for comparing patches, which similarity metric is best? SAD, SSD, NCC?
Sum of absolute differences, SAD, and sum of squared distances, SSD, are simple and fast, but very sensitive to changes in lighting or exposure between the images. Normalized cross-correlation, NCC, is generally much more robust to these changes. It calculates the correlation between patches after normalizing them by their mean and standard deviation, making it invariant to linear changes in brightness and contrast. Usually preferred, though more computationally expensive.
Okay. We talked about attention mechanisms in NLP with transformers. They're used in computer vision, too.
Absolutely. Similar idea. Instead of treating all parts of an image or all feature channels equally, attention mechanisms allow the model to learn to focus on the most relevant parts for the task at hand.
Like focusing on the object you're trying to detect.
Exactly. Spatial attention learns to weight different regions of the image, or feature map, more heavily. Channel attention learns to weight different feature channels, like those detecting specific textures or colors, based on their relevance. It's all about adaptive weighting, often using similar query key value concepts as in transformers to make processing more efficient and effective.
Cool. Okay, let's move into some advanced model architectures and concepts. The sources briefly revisit representation learning.
Just a quick reminder that a major goal, especially in deep learning, is having the model automatically learn good, useful features or representations of the input data, rather than us having to handcraft them. Things like autoencoders or just the intermediate layers of deep networks are learning representations.
And then the big one, transformers.
Yeah, originally for language, now everywhere. The core mechanism is self-attention. It allows each element in a sequence, like a word token or later an image patch, to look at all other elements in the sequence and calculate how relevant they are to understanding itself.
Using queries, keys, and values.
Right. Each element generates a query, a key, and a value. The query of one element interacts with the keys of all elements to produce attention weights. These weights determine how much of each element's value should be summed up to produce the new representation for the original element. It learns contextual relationships dynamically.
And they need positional encoding because attention itself doesn't know the order.
Exactly. Self-attention treats the input as a set. Positional encodings, fixed or learned vectors added to the input embeddings, give the model information about the position of each element in the sequence. Feed-forward networks are also part of the standard block, applied independently to each position's representation to add nonlinearity and processing capacity.
The typical transformer architecture involves encoder blocks and decoder blocks. What's in an encoder block?
Usually it's a multi-head self-attention layer, followed by a position-wise feed-forward network. And crucially, there are add and norm layers around both.
Add a norm.
Two parts. Add refers to the residual connection. The input to the layer is added back to the layer's output. This helps gradients flow through very deep networks, preventing vanishing gradients. Norm refers to layer normalization, which normalizes the activations across the features for each sequence element independently. This stabilizes training.
Okay, and the decoder block. Similar but different.
Similar structure, but with additions for sequence generation. It typically has two attention layers. First, a masked multi-head self-attention layer. The masking prevents positions from attending to subsequent positions crucial for autoregressive generation, where you can only depend on previously generated tokens.
Can't see the future.
Right. The second attention layer is cross-attention. Here, the queries come from the decoder sequence, the target sequence being generated, but the keys and values come from the output of the encoder, representing the source sequence. This allows the decoder to focus on relevant parts of the input sequence while generating the output. Then there's usually a feed-forward network, again with add and norm throughout.
The sources compared GPT and BERT. What's the main difference in structure purpose?
Generally, GPT, generative pre-trained transformer models, are often decoder-only architectures. They excel at autoregressive tasks, predicting the next word token in a sequence, making them great for text generation. BERT, bidirectional encoder representations from transformers, typically uses the encoder part of the transformer. It's designed to learn deep bidirectional representations by considering both the left and right context simultaneously, using techniques like masked language modeling during pre-training. This makes BERT very good for tasks requiring a deep understanding of the full context, like classification, question answering, or named entity recognition.
And the scale of these models. Llama 70B parameters. It's mind-boggling.
Absolutely massive, 70 billion parameters. Even storing that takes hundreds of gigabytes. Training involves two main phases. Pre-training on enormous, diverse data sets, like huge chunks of the internet, where the model learns general language patterns. Then fine-tuning or alignment on smaller, curated datasets to adapt the model for specific tasks or desired behaviors, like following instructions or being helpful and harmless.
And tokenization is the first step, right? Breaking text into pieces.
Yep. Models don't operate on raw characters. They use tokenizers, like byte pair encoding (BPC), to break text into common words or subword units, tokens. The model then learns an embedding vector for each token in its vocabulary. The size of this embedding matrix, vocabulary size times embedding dimension, is a significant chunk of the model's parameters. Calculating parameters for the attention layers and the feed-forward MLP layers also involves matrix multiplications based on embedding size and hidden dimensions.
So how do we take this transformer power and apply it to images? Vision transformers, VIT.
VIT was a key breakthrough. The core idea is, treat an image like a sequence of patches. You divide the input image into a grid of non-overlapping patches, say 16 by 16 pixels. Flatten each patch into a vector, linearly project these patch vectors into an embedding space, add positional embeddings to retain spatial information, and then feed this sequence of patch embeddings directly into a standard transformer encoder.
No convolutions at the start?
Not in the original VIT, no. It relied entirely on self-attention between patches. Finally, an MLP head is attached to the output, often using a special CLS tokens representation for the final classification task.
And related models like DTR for object detection?
Yeah, DTR, detection transformer, and similar models adapt the transformer architecture for tasks beyond classification, like object detection or segmentation, often combining CNN backbones with transformer encoders decoders to output bounding boxes or masks.
Training these huge vision models seems like it would need immense labeled datasets, but self-supervised training helps here too.
Massively. Self-supervised learning, SSL, allows models to learn powerful visual representations from vast amounts of unlabeled image data. The key is to devise a pretext task, where the model learns by predicting some property of the data from another part of the data itself. The sources highlight two prominent SSL methods for vision, often used with VOTs, BYOL and DINO.
BYOL, bootstrap your own latent. How does that work without labels?
BYOL uses two networks, an online network and a target network, initially identical. You feed two different augmented views of the same input image to the networks. The online network processes one view and has an extra predictor head. Its goal is to predict the representation produced by the target network for the other view.
Predicting the other network's output.
Yeah. Crucially, the target network's weights are not updated by backpropagation. Instead, they are updated slowly as an exponential moving average, momentum encoder, of the online network's weights. The magic is that BYOL learns strong representations without using negative pairs. That is, without explicitly pushing representations of different images apart. It avoids collapsing to a trivial solution, outputting the same thing for all images, through the predictor head and the momentum encoder dynamics.
Interesting. And DINO, distillation with no labels.
DINO also uses a student-like online and teacher-like target network setup, with the teacher updated via momentum. But the student is trained to directly match the teacher's output distribution, after softmax, for different augmented views of the same image, using a cross-entropy loss. It's like knowledge distillation, but the teacher is generated from the student itself over time.
How does DINO avoid collapse?
It uses a couple of tricks. Centering, ensuring the teacher's average output over a batch is centered, preventing dominance by one dimension, and sharpening, using a lower temperature in the teacher's softmax to make its output distribution peakier, encouraging the student to be more confident. It also benefits strongly from a multi-crop strategy. The teacher sees larger global views, while the student sees both global and smaller local views, forcing it to learn representations consistent across different scales.
And the sources mention DINO features showing segmentation properties.
That was a striking result. Even though DINO wasn't trained for segmentation, the attention maps of VYTs trained with the DINO often clearly highlight object boundaries. It suggests the self-supervised task forces the model to learn about object structure implicitly. DINO also showed strong performance on downstream tasks, especially K&N classification using the learned features.
So both BERT and DINO are clever ways to use unlabeled data, twin networks, momentum, and augmentations to learn powerful features.
Okay, the sources list many other model architectures too, like the RCNN family for object detection. Right, that shows an evolution. RCNN started by using selective search to propose regions, then ran a CNN on each. Fast RCNN improves speed by running the CNN once on the whole image and using ROI pooling to get features for proposed regions. Faster RCNN went further by integrating the region proposal step itself into the network using a region proposal network, RPN. And Mask RCNN extended faster RCNN to also predict segmentation masks for each detected object, instance segmentation. The table summarizes these nicely.
And contrasting that with YOLO.
YOLO, you only need once, takes a different approach. It's a single-shot detector. Divides the image into a grid, and each grid cell directly predicts bounding boxes and class probabilities for objects centered in that cell, much faster than the RCNN family initially, though sometimes less accurate on small objects. The sources mention the latest YOLO 10 uses a novel dual-label assignment strategy during training that helps avoid the need for non-max suppression, NMS, during inference, potentially speeding things up further.
Other architectures mentioned, ResNet.
Key innovation: residual connections, or skip connections. These allow gradients to flow more easily through very deep networks by providing shortcuts, enabling the training of networks with hundreds or even thousands of layers. Huge impact.
Well met.
Focused on efficiency for mobile devices. Uses depth-wise separable convolutions, which split a standard convolution into two steps. A depth-wise convolution, filtering each input channel independently, and a point-wise convolution, one-by-one convolution to combine channels, drastically reduces parameters and computation. The calculation example shows the difference.
And EfficientNet.
Took a more systematic approach to scaling networks. Instead of just making networks deeper or wider arbitrarily, EfficientNet used a compound scaling method to uniformly scale network depth, width, and image resolution using a learned coefficient. Often achieves better accuracy for a given computational budget. Use swish activation and techniques from MobileNet.
It's clear these ideas are spreading. The mention of foundational models for robotics suggests these large pre-trained models are moving into that domain too.
Definitely a trend. Applying large-scale representation learning and architectures like transformers to robot perception and control.
Speaking of leveraging large models, our RAG, Retrieval-Augmented Generation, seems crucial for making LLMs more useful in practice.
Absolutely. R grounds LLMs in external, often up-to-date or private knowledge. The NVIDIA diagram shows the typical flow. User asks a question, prompt. This goes to a retrieval system.
Using tools like LlamaIndex or LangChain?
Right. These orchestrate the process. The query is used to search an external data source, like enterprise data, documents, databases. This data needs to be pre-processed and stored, usually in a vector database, like Milvus.
Using embedding models to turn text into vectors first, like E5 text embedding.
Exactly. An embedding model creates vector representations of the data chunks. The vector database allows fast similarity search to find chunks relevant to the user's query. These retrieved chunks are then passed along with the original prompt to the LLM, like Llama 2, for augmented generation.
So the LLM uses the retrieved context to generate a more accurate, grounded response.
Precisely. It reduces hallucination and allows the LLM to answer questions based on information it wasn't originally trained on.
Now, comparing those embedding models, CLIP text encoder versus E5 text embedding, they seem optimized for different things.
They are. The table highlights the differences. CLP was trained primarily on 400 million image caption pairs, using a contrastive loss to align text and image embeddings in a shared space. It excels at cross-modal tasks relating text to images, zero-shot image classification, text-to-image retrieval. Its text encoder is often GPT-2-like.
And E5.
E5 models are trained contrastively, but on large text pair datasets, like question-answer pairs, text similarity pairs. Their focus is purely on text similarity and retrieval. They're typically BERT-based, use techniques like average pooling for embeddings, and often benefit from adding task-specific prefixes, like query or passage, to the input text before embedding. They're designed to be strong standalone text embedders for semantic search.
Different tools for different jobs. Okay, a really important topic. Addressing biases in ML, the sources cite some landmark work.
Yes, crucial area. The work by Joy Buolamwini and Timothy Gebru famously showed significant disparities in the accuracy of commercial facial recognition systems, particularly lower accuracy for darker-skinned women compared to lighter-skinned men. This highlighted how biases in training data or model design can lead to harmful outcomes.
And bias shows up in language models, too.
Definitely.
Yeah.
Research by Tolga Bulukbasi, Adam Kalai, and others demonstrated how word embeddings, like Word2Vec, trained on large text corpora, can absorb and reflect societal biases present in that text, associating certain professions with specific genders, for example.
The Stanford group's work, Nikhil Garg, James Zhu, etc., showed how analyzing these embeddings can reveal societal trends.
Yeah, they showed that changes in word embeddings over time could mirror historical societal shifts and biases. Analyzing things like the top K nearest neighbors to words can surface these embedded associations.
The term redundant encoding was mentioned as a challenge in studying bias.
Right. This refers to the idea that even if you remove a sensitive attribute, like race or gender, as a direct input feature, other correlated features might still implicitly encode that information. This makes it hard to truly debias a model just by removing the obvious sensitive feature, as the bias can still creep in through these redundant pathways. Makes auditing and mitigation harder.
And Cynthia Rudin's work on interpretable AI offers a different path.
Instead of building black boxes and trying to explain them later, explainable AI, interpretable AI aims to build models that are inherently understandable from the outset. Think simple linear models, decision trees, or rule lists. This is vital in high-stakes applications like healthcare. The CHAIS score for stroke risk is an example of an interpretable model physicians use, or criminal justice, where transparency and trust are paramount.
Makes sense. Okay, pulling back a bit, the sources outline a general ML workflow for tackling problems.
Yeah, a practical roadmap. First, really understand the problem. Is it regression? Classification? What output do you need? Then, determine if ML is appropriate. Maybe simpler heuristics or rules work fine. Or maybe an ensemble or post-processing is needed. Then find or create data bets. Crucially, perform exploratory data analysis, EDA, to understand the data's properties, patterns, outliers.
Then preprocessing.
Right. Data normalization or standardization. Then choose or build an initial architecture. Start simple. Iteratively add complexity as needed. Use regularization, L1, L2, dropout, etc., to prevent overfitting. And finally, evaluate rigorously using methods like k-fold cross-validation to get a reliable estimate of performance on unseen data.
For object detection specifically, mean average precision, MAP, is the go-to metric.
Yes, MAP is the standard benchmark. It captures the average precision of the detector across different levels of intersection over union, IOU threshold, how much overlap is required between the predictive box and the ground truth box to count as a correct detection. It's averaged over all classes and usually multiple IOU thresholds. Higher IP is better.
Okay. And once a model is trained, making it run fast is key. Optimization methods for runtime. Mixed precision training.
This uses a combination of lower precision, like 16-bit floating point, FP16, and higher precision, FP32, arithmetic, during training or inference. Many operations, like large matrix multiplies and deep networks, can be done much faster and with less memory using FP16 with minimal loss in accuracy. But some operations, like accumulating gradients or certain activations, might need FP32 to maintain stability and precision. Modern hardware like NVIDIA GPUs has specialized cores for accelerating FP16 math.
So it's about using the right precision for the right job to speed things up. And TensorRT?
TensorRT is NVIDIA's software library, specifically for optimizing trained deep learning models for inference deployment. It takes a trained model graph and performs various optimizations like layer fusion, combining multiple operations into one, kernel auto-tuning, picking the fastest implementation for the specific hardware, and precision calibration, optimally using lower precision like FP16 or INT8. It works on just-in-time, JIT, compiled graphs. The sources mention different ways to get these graphs, like tracing or scripting in PyTorch.
Okay. A quick dip back into robotics. Inverse kinematics versus inverse dynamics.
Two fundamental problems in robot control. Inverse kinematics, IK, asks, if I want my robot's hand and effector to be at a specific position and orientation in space, what angles do all the joints in the robot's arm need to be at? It's a purely geometric problem, finding joint configurations for a desired pose.
And inverse dynamics ID.
Inverse dynamics asks, if I want the robot's joints to follow a specific trajectory, positions, velocities, and accelerations over time, what torques or forces do I need to apply at each joint to achieve that motion? This considers the robot's dynamics, masses, inertias, gravity, friction. It's about calculating the required forces for a desired movement. Uses methods like Newton-Euler or Lagrangian dynamics.
Got it. Geometry versus forces motion. Now, focal loss. That was mentioned for imbalance classification.
Yes, super useful when you have, say, many negative examples and very few positive examples, like detecting a rare disease or fraud. Standard cross-entropy loss can get overwhelmed by the numerous easy negative examples, leading the model to perform poorly on the rare positive class.
How does focal loss help?
It modifies the standard cross-entropy loss by adding a modulating factor, typically 1 pt gamma, where pt is the model's predicted probability for the correct class, and gamma is a focusing parameter, usually gamma 2. If an example is easily classified, pt is high, this factor becomes small, downweighting the loss contribution from that easy example. If an example is hard, pt is low, the factor is close to 1, keeping its loss contribution high. This forces the model to focus more learning effort on the hard-to-classify examples, which are often the rare class examples. It often includes an alpha term, too, to directly weight the positive and negative classes.
Smart way to rebalance focus. And the principle is from that old efficient backprop paper by LeCun et al. Still relevant.
Many of them are bedrock principles now. Things like using mini-batch gradient descent, not full batch or pure SGD, normalizing inputs like standardization, using activations like 10H or ELU instead of sigmoid to avoid saturation, using smart weight initialization strategies like Xavier He we discussed, and using adaptive learning rates. These are all standard best practices derived from understanding backpropagation dynamics.
And finally, revisiting the advantages of stochastic learning, SGD mini-batch, over plain batch GD.
Yeah, worth summarizing. It's much faster per update. The inherent noise can help escape poor local minima and sometimes find better, flatter minima that generalize better. It can track changes in data distribution over time, online learning, and it handles redundant data, like from data augmentation, more effectively. Batch GD gets less benefit from seeing slightly augmented versions of the same data over and over in one epoch. The optimizer parameters table, eta, gamma, beta 1, beta 2, etc., shows how different hyperparameters control the behavior of optimizers like ATOM or RMS prop managing learning rates and momentum to navigate the loss landscape effectively.
Wow. We have covered a tremendous amount of ground in this deep dive, haven't we? I mean, from the absolute basics, AI, ML, deep learning distinctions.
Right, through supervised, unsupervised learning mechanics, the math-mind optimization, the guts of neural nets and backprop.
All the way to advanced stuff like transformers, RL strategies, applications in CV and robotics.
Yeah, and seeing how core concepts like covariance, loss functions, regularization, initialization all play critical roles. It really is fascinating how these complex systems are built up from, well, relatively fundamental mathematical and statistical ideas when you break it down.
It really is. Which I guess brings us to a final thought. Given everything we've discussed, the power of these techniques, but also the challenges like bias, deployment complexity, understanding what these models are truly learning, what do you think is the most critical piece still missing, or maybe the area needing the most exploration, to really unlock that next level of intelligence or capability in these systems? Something for us all to chew on.